Sweet. Okay. Most of this talk that just started like a minute ago is going to be actually about the first point, so how to talk to ML models, but there's also like infrastructure in LLVM for supporting training. I'm not going to talk about training because there's nothing in LLVM. Okay. So, think about a ML model as a function. Okay, just think about it like that. And it's written in a domain-specific language. So, you need some sort of an interpreter or some way to evaluate that function if you want to use it. So the abstraction for that is ML model runner, very inspiredly named. It lives in analysis. Everything in ML deals with tensors. Tensors are big buckets of data. The tensor specification, so kind of like a type for that, is called tensor spec. It also lives in analysis. It has a name because we do name-based binding. That's bad, but just hold on a second. And then it has basically a type and a size, like a shape. We don't really care about the shape more than just the fact that, we need buffers that size, right? So high level, how do you, on the compiler side, all that I really care about is calling this function. I said that we have an abstraction. You have to pick an abstract, like an actual implementation of that, and all of them take as a parameter, among other things, but they have to take as a parameter this list of tensor specs, and the order in which the tensor specs are given there is how we're actually going to reference them from now on. So we stop with the name-based binding because that's inefficient, and we move to using indices. And then just basically what to do is like you say, hey, give me the tensor at index whatever. You get a buffer of the appropriate size. You fill it up with data of the appropriate scalar type. And when you're done doing that, you say, hey, runner, evaluate, and you treat the value as you should. And there's examples in detail in those two places. So the contract with an implementer of ML model runner, so if you implement that thing, what you gotta do is at construction time, figure out what your buffers are for these tensors, and you populate this protected member called input buffers, because from there on, nothing is virtual anymore. So get tensor is basically it's non-virtual, and it just fetches whatever you put there. The tensor buffer lifetime must be the same as the model runner's lifetime. So basically, these things don't move out of there. And the only thing is that the data is in row major ordering. That's not surprising. There's also like a story about how we do versioning, where you can actually add more features on the compiler side and then still use a model that doesn't know them until you get to train that model to know them. 3 implementations in LLVM for ML model runner. The first one is basically what we use in production. You need special CMake magic. You need to pass at minimum that flag over there that points to an AOT compiler, so ahead of time compiler. This is all TensorFlow specific from this point on. There's a CMake function called tf-find and compile. If you look at it, it has basically like you can have other CMake flags that say, well, which model do you want to actually embed? You get a generated, like native code like x86 or ARM or whatever with a name that you gave it. And then you just instantiate release mode model runner with that particular type. And all that the model runner implementation does is it adapts one native interface to another one. The second one is for researchers. It's like a gym interface. What you do is you give it 2 files. And basically all that it does is when you call evaluate on this model runner, it dumps the tensors to the first file, to the one that you can push data out, and then it waits blockingly for data to come from the other one. This has no dependencies, it just works. Well, if you opt into working with it, it's not for production, of course. There's examples there that show like a toy example, like basically there are test examples with like a full agent that, like works with the compiler, starts it, talks to it, all of that. Come on, okay. We do have another serialization protocol because, YOLO. The serializer is in C++, of course, because that's all we care about. We push data out, and we read very little scalar, so we don't need something too magical for that. The deserializer is in Python. It's just a reference that we use in tests. Write your own. The protocol is very simple. It's basically a bunch of JSON that says how the data will look like, and then data dumps, like, mem copied down to that file. The file can be a name pipe, so it's pretty efficient. Finally, we have an interpreter. So this again requires CMake. It's again TensorFlow specific. The second one wasn't, but this one is. Thanks to Peter Jose for making this scenario quite easy, because all you gotta do is like basically run a couple of commands and then CMake with a -C, and you got your TensorFlow Lite interpreter. And then the only big thing here is that you can pass the model from the command line. There's a couple of nuances that I'm not going to get into details here because I don't have time, but if you look at the examples there, it'll become quite obvious. Like you have to like convert a safe model to TF-Lite basically, and we have a utility that we use during tests. So corpus collection, the whole point of corpus collection is that you want to be able to replicate your setup that you have when you build your project, but in a way where you can take any module, like, I mean, training things like to pick up things randomly, so you can pick any module and recompile it and get bit identical things just for a baseline to what you'd get in production for that object file, right? So we use something that Apple did that basically, like allows you to basically capture the IR right before the optimization pipeline and the command lines being used, and then you can replay those. This works with Clang. Logically, you build your project as you would, but you pass additional C++ and C or C++ flags, and then you scrape the object files for these two sections. That's how you can scrape them. There's also like support in a script reference there for popular, like build systems like the ones that produce compile commands.json, for example, that we all know. CMake does that, or GN. Also linker.params. Okay, so what are those flags? There's 3 scenarios that we added support for. Vanilla Clang compilation, you just add that flag. ThinLTO distributed, which we use at Google. And then ThinLTO local, that is, like if it's not distributed. And actually, in the last case, you don't have to scrape anything because it actually straight dumps, the IR code to the disk. You don't have to go for fishing for it. So I mentioned what the corpus is. And then when you use it, you basically pick any of these things. Like you pick the BC, you run it with the commands that are in that command file, and you get bit identical output. And of course, now when you start training, you can do other things to it, and you're not going to get bit identical output, of course. In the ThinLTO case, either of the two, so local or distributed, you got to pass this extra flag, because the whole point of ThinLTO is that you don't want to go and tell an ML infrastructure that, hey, you got to crack open IR just to find what you got to import, right? So we catch the IR after import happens in ThinLTO, but before any optimization. But then you have to tell, hey, ThinLTO, don't bother importing anymore because there's nothing to import. You might not even see the files to be imported. Okay. Last but not least, so, I mean, important for ML training is having like some sort of a reward signal. For size that's trivial, for register allocation, we use something naive that kind of doesn't really work that well. So I'm not going to talk about that. The direction forward that we want to have is LLVM CM. There's an RFC that Diane Dalmeida, actually he talked anyway yesterday, he had like a lightning talk. But, like for that, you actually need the performance profile, because otherwise, how can you calculate reward? Like, how can you differentiate between policies that are very much about performance? Today, what we have is we can dump the last seen by the compiler, like in asm print, like the last seen machine basic block frequencies with those flags there. Aidan Grossman added that. But Mika Weston has a much better proposal. There's an RFC that she put like last week, I think. Oh, hi, last week, right? Right. It's called PGO Accurate Metrics. If you search for that, it's a much better proposal, and we'll move to that, but that's what we have there right now. So what's next? First, we want to drop, we discovered, thanks to Natasha Kononenko and Jacob Hegna, that we don't even need an ahead of time compiler dependency, and we can use emit-c. I think there was a talk about emit-c. We want to use that. There's a patch. We want to land it. We just didn't have time. We also want to explore variable tensor support, but we don't have scenarios right now. We know that there is some work on that, but we just didn't see something that we can use. And maybe some of the boilerplate that we are today using is a bit, well, I said it's boilerplate, so right. You can get in touch with us in the usual way. There's a tag, ask questions there, tag it with that. There's also like a pull request. If you look in the pull request themes for MLGo, you can join there and see any changes that happen to the source code. That's it. I think I'm on time, right? Cool.